Okay, hello all you donkeys out there. We've been learning about electrochem, a little bit of redox and galvanic cells. So let's move on and let's take a look at this consider. We've got a galvanic cell composed of iron and nickel. What is the um, standard reduction potential for this cell? Okay, I'm not sure I remember much about this stuff, so maybe we ought to talk for a second and draw our galvanic cell, right? So this is kind of our galvanic cell. We've got a couple of half cells, and we have some electrodes in there, and these electrodes are in contact with one another through a wire. And we have a salt bridge, right? And one of these is going to be the oxidation half cell, and the other is going to be the reduction half cell. And what did we say from our question? We had what going on here? Let's go back for a second. We have iron 2 and nickel. So we have iron 2, and it might reduce to form iron. And we have nickel 2, and it might reduce to form nickel. Now, here's the question. Which of these is going to reduce? Because one of these is going to reduce and go into our reduction half cell, and one of these is going to oxidize and go into our oxidation half cell. And that's where we turn to this idea of standard reduction potentials, right? Standard reduction potentials. It's a lot to write, so I just write down E prime red, a standard reduction potential. Now, what's that standard reduction potential tell me? This tells me the likelihood tells me the likelihood of a species to reduce. The higher the value, the more likely to reduce. More likely to, better move, I'm going to run into that box there, to reduce. Good. Now, where do we find these standard reduction potentials? Well, the beauty of all of this is that someone has done the work for us. In this case, Brown, LeMay, and Prentice Hall have these standard reduction potentials for us. And so all we have to do is find the values. So we'll come around here. We need to find what? Nickel. We need to find nickel and iron. So let's find nickel or iron, either one, iron, Fe. Ooh, come way down here and we find iron. Here's my iron. It is a negative 0.44. Let's go back to our previous slide, and we have a negative 0.440 volts. And then we need to find our value for nickel. Where's nickel? Nickel right here. Looks like a negative 0.28. So a negative 0.28. So I have a negative 0.28 volts. So we compare these two, and I see that this is actually a higher value. A negative 0.28 is a higher value than negative 0.44, which means nickel will reduce. So that means I'm going to have nickel 2 in my solution, and this is going to be nickel, which means that that is going to be my cathode. The lower value is going to oxidize, so that means my iron is going to be in my oxidation half cell, and that my and this will be called what? My anode, and my electrons will flow from my anode to the cathode, right? And so that is our review. Now, the question that was really asked in the last slide was, what is my E cell? Well, my E cell is the is the electromotive force for this cell. What is it? Is the driving force, the thing that makes this cell actually function. And the way we get that is that the standard reduction, the standard potential, cell potential, is equal to the standard reduction potential at the cathode minus the standard reduction potential at the anode, right? And so that means We find the standard reduction potential for the thing that is reducing, and another way to think about the anode or the cathode is it's for my half reduction cell, and the anode would be my half oxidation cell. Good. So how do I figure out the cell potential here? I'm going to find where's my cathode, where's my half reduction. We said my half reduction cell is my nickel, so I'm going to write down the value for my nickel over here, and it's going to be a negative 0.28 volts minus, right, the value for my oxidation half cell, which will be my lower value. So that will be minus a negative 0.440 volts. And that looks to me like that is a 0.16 volts, and that is a positive value. There we go. Good. All right. That looks simple enough. So let us see if I answered the question. Yeah, I think I did. All right, you guys go to this one. Consider the galvanic cell composed of copper and zinc. You guys tell me what the standard reduction cell is. Bring me back when you are ready. Okay, that shouldn't have been a problem. We have our cell, and I kind of always like to draw these for myself. You guys may not need it. So here's my cell, right? I have my two electrodes. They're attached. I have my salt bridge. I have some solutions in here. One of these is going to be a half oxidation cell, and the other is going to be a half reduction cell. And I have to figure out which of these two dogs is going to oxidize and which is going to reduce. And to do that, I need to go to my standard reduction tables, right? And so when I look at my copper, I'm going to go look at my copper. Where's copper? Right here. Okay, copper. Na 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 na. Copper, 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 copper. Oh, copper right here. Copper right here, right there. 0.337. 0.337. We better go back here and write it down before I forget. So this is a 0.337 volts. And what's my zinc? Anybody have an idea what zinc is? We better go back and check. Zinc, yoink. It's like a negative something. It's a negative right there. Zinc, 0.763. Okay, 0.763. Negative 0.763 volts. And so now which one of these is going to be reducing? The one with the higher value is going to be reducing. So my reduction half cell is going to have the copper in it. That will mean my copper, solid copper, is the cathode. And that would mean my zinc is going to be in the oxidation half cell. My zinc is going to be my anode. And as always, electrons flow from the anode to the cathode. My standard cell potential will be equal to the standard reduction potential at the cathode minus my standard reduction potential at the anode, which would be equal to what? How about a 0.337 minus a negative 0.763. So I think I can do that in my head. 337 plus a 0.763. It looks like a 0 carry the 1, 0 carry the 1, 0 carry the... Oh my goodness, is that right? I think, there we go. I think my answer is 1.100 volts, right? Good. All right, let's make sure 7 and 3, 10 carry the 1, 9, 10 carry the 1, 10, there's a 1 there, carry the 1, 1.0. Good. So that is my standard cell potential. Great. Now the cool thing here is this idea of standard cell potentials or potentials are not only the driving force for galvanic cells, but also for all redox reactions. So anytime I have a redox reaction, I can anytime I have a possible reaction occurring, I can determine if it will occur by looking at my my potential, my reaction potential. So I can calculate a reaction potential for a redox reaction, not just for a galvanic cell. So let's go back up here to our notes. We have these notes going on here, and boy, is that a mess, isn't it? Let's come down here and let's get some prettier notes here. Okay, so we have our, I gotta go to yellow now. I have my cell, I have my potentials, right? And my potential I can use for a cell, or I can calculate a potential for a redox reaction. And the way I can calculate my cell potential, we said, is that my E cell potential, standard E cell potential, is equal to my standard reduction potential at the cathode minus the standard reduction potential at the anode. All right. Now, how do we do it for a normal redox reaction? Well, we get a standard potential for the reaction will be equal to the standard reduction potential of my reducing species minus the standard reduction potential of my oxidizing species. Hey, that's really the same thing we were talking about before, right? So here we go. Let us work that problem out. Good. So I look at this, and I have to find out, okay, do I have something oxidizing or reducing? And the answer is, of course I do. Which of these is oxidizing and reducing? So I have mercury, which is 0, going to +2. That looks like it's oxidizing. So my mercury is going to oxidize. Now, here's the weird thing is we have to look at it not as an oxidation, but as a reduction because my potential, my tables are in reduction. So I have to look at the reduction of that. So I'm going to say mercury 2 plus 2 electrons is going to go to mercury liquid. There we go. Now I have to look that specific reaction up in my table to find the standard reduction potential, even though it is really oxidizing. Good. And now what's reducing? Well, what's reducing is my iodine is reducing to 2 iodides. There we go. So let's find those potentials in the table. Here's our beautiful table. We need to find mercury. We'll look at mercury's right there. When I look at mercury, what do I see? I see 0.789. So let's go write 0.789 before I forget. 0.789 volts. And then, did you guys check it? Did you guys catch that iodine? I didn't catch the iodine. I'm going to have to come back. Where's iodine? Right. Oh my gosh, it's right there. 0.536. 0.536. 0.536. No, 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 no. There we go. 0.536. So let's go back. 0.536. 0.536 volts. And what did we say? We said, hey, my standard potential for the reaction is equal to my standard reduction potential for the reducing species minus the standard reduction potential for the oxidizing species. Good. So what did we say was my reducing species? My reducing species was the iodine, 0.536 volts, minus what was my oxidizing species? And it's the standard reduction of potential for that oxidizing species. So you write down the number from the table. Don't do any changing of sign or anything like that. That'll just cause you problems. Good. So I take these two numbers. What do I get? 0.536 minus 0.789. And it looks to me like I get a negative 0.253 volts. Okay, cool. So I have a negative volt. Negative voltage. Which brings us to our next question. Is this reaction spontaneous? Okay, so let's talk a second about spontaneity. We learned a little bit about spontaneity previously, but let's kind of codify that here. We could talk about spontaneity, and we could relate it to my E. Okay, oops, kind of need yellow here to see. So we can talk over here about spontaneity, spontaneity, and we might want to know what spontaneity means. Let's get rid of this so we can have some more space. Yoink! Magic, I love magic. Spontaneity. So let's go with the definition. What is spontaneity? It means essentially, will it happen? Not how fast, but will it happen eventually on its own? So that's what we mean by, I guess that's not really a definition. This is the critical question related to spontaneity. So really, I guess a definition, that's really a mess. Let's go back and clean this up. What is a spontaneous process? A spontaneous process is one which occurs eventually on its own. We can get rid of that question mark. Oh, can't get rid of, there we go, on its own. On its own. That is a spontaneous process. It does not have anything to do with how fast, but given enough time, a million years, will this happen? The answer is yes, then it is spontaneous. Another term we use for this, we say it is thermodynamically thermodynamically, thermodynamically, how about that? Thermodynamically favorable. A spontaneous reaction is one that is thermodynamically favorable. Good. Now, how do we determine whether something is thermodynamically favorable? It's real simple here. Let's go down here. Yoink. Yoink. If E is greater than 0, if it is positive, then the forward reaction is spontaneous. If E is negative, then the reverse reaction is spontaneous. Good. Piece of cake, right? Easy. Let's go back, answer our question. Yoink. What did we find? We said that we had a negative value for, we had a negative value here. That means what? My reaction is not spontaneous in the forward direction. So that means if I would put some mercury in with some iodine and give it a long time, nothing would happen. Good. You guys do the last one, and we will be done with this set. All right, you guys consider this one. Come back and get me when you're ready. Wow, this one looks pretty complicated. Okay, so I might need some help here. The easy one, right, is I have manganese going to manganese 2 plus. That looks like oxidation. So I have manganese oxidizing, and the reduction reaction is going to be manganese 2 plus 2 electrons going to form manganese solid, and I'm going to get some kind of reduction potential over here, right? The other one's a little more complicated. It looks what's left. I have 4 H pluses plus H2SO3, and that is going to go over here to some sulfur, a sulfur, and 3 waters. Now, if we're lucky, the rest of this will show up in our table. So let's go see if we're lucky. Come back to our table, and I'm looking for sulfurous acid. So let's find sulfurous acid. H2SO3. Do you guys see H2SO3 anywhere? H2SO3, H2, here's H2SO3. Look at that, H2SO3 going to water and sulfur. There we go. And it has a 0.45. So 0.45. Good. So we found it, 0.45. Let's come back up. Let's drop this in here. And I have, this is a positive 0.45 volts. And what is my manganese? Let's go back, find manganese. Manganese, yoink, where's manganese? Oh, right there's manganese. A negative 118. Okay, a negative 118. A negative 118. So this is a negative 1.18 volts. Good. We said this is my oxidizing. That means this is my reducing species. So we are going to get my reaction potential. I'm going to take my reduction, the standard reduction potential for my reducing minus the standard reduction potential for my oxidizing, and that's going to be 0.45 minus a negative 1.18 volts. And what do I get out of that? Use my magic handy dandy TI-30XA. 0.45 minus a minus would be a plus 1.18, and that looks to me like I get a 1.63 positive volts. And the question is this spontaneous? Well, since I have a positive value here, the answer is yes. This happens spontaneously. All right, I hope that helps. Enjoy your day, folks. Bye-bye.